Question 11 says N1 moles of an ideal gas with rigid diatomic molecules are kept in a container at temperature T. Now the temperature is increased to 2T, and in the process N2 moles of the gas get converted to monatomic gas. The change in the total kinetic energy of the gas is. Well, question is clearly from the topic kinetic theory of gases, and it's concerned with the internal energy of the gas. In fact, it's given that the molecules are rigid diatomic molecules, but at temperature 2T, some of these molecules are getting dissociated. So what's the importance of the term rigid diatomic molecule? Well, it means that the degree of freedom is to be taken as 5, 3 for translational and 2 for rotational. So the initial internal energy of the gas, we can call it, in fact, and all of it is the kinetic energy, in fact. So Ki is in fact Ui. Ki means initial kinetic energy, which is initial internal energy, and this is equal to N1 into degree of freedom is 5, so 5 R by 2 T. This is the initial kinetic energy of the molecules, and well, the temperature now is increased to 2T, and also what is happening is that N2 moles of the gas are converting into monatomic gas. So that means Kf, which will be same as Uf, the final internal energy, is equal to, now the number of diatomic moles will now be equal to N1 minus N2. So it's N1 minus N2 into 5R by 2, and now the new temperature is 2T, so it is 2T plus, now N2 moles have converted to monatomic gas, so that means we now have 2 N2 moles of monatomic gas at that temperature. So the internal energy of that part is 2 N2, and for monatomic gas the degree of freedom is only 3, so it is 3 R by 2, and the temperature is 2T. So this is the final kinetic energy. Let's simplify the expression for the final kinetic energy. So we have Kf is equal to N1 minus N2 into 5R T, and well, the other one is 6 N2 RT. So that is 6 N2 RT, and so Kf minus Ki, which is the change in the kinetic energy, is equal to this minus this, and if we do that, we have N1 by 2 into 5 RT plus N2 RT. So this is what it simplifies to, and among the options, well, this is clearly matching with option 2, so option 2 is correct for question 11. Let's go to the next question now. Question 12 says a thermally insulated vessel contains an ideal gas of molar mass m and adiabatic exponent gamma. It is originally moving with speed v, and its speed is suddenly reduced to v by root 2. The temperature of the gas increases by. Well, this question is also based on kinetic theory of gases, and well, the kinetic energy of the ordered motion, the velocity v of the vessel is what we call the ordered motion of the gas, and the temperature is a reflection of the random motion of the gas. So in this particular case, what is happening is the kinetic energy of the ordered motion will convert into the kinetic energy of the molecules of the gas, and that means the temperature will increase. So let's look at the loss in the kinetic energy due to ordered motion, and the expression for that is simply half total mass m. Now total mass m will be a number of moles into molar mass, so small n into small m is the total mass of the gas, and its initial kinetic energy was this into v square, and the final is this into v by root 2 whole square. That means it is v square by 2. So this is the loss in the kinetic energy, and this loss in kinetic energy is in fact equal to delta U, and expression for delta U then will be the total number of moles, which is N, into CV into delta T. We can see that the N is cancelling on both sides. So what we have is half M, where M is the molar mass, into V square by 2 is equal to R upon gamma minus 1 into delta T. And so we can see that delta T, the change in temperature of the gas, is equal to mv square into gamma minus 1 divided by 4r. Well, if we look at the expressions, we can see that it is clearly matching with option 4. So that means for question 12, option 4 is correct. Let's go to the next question now. Question 13 says two non-reactive monatomic ideal gases in a container have their densities in the ratio 2:3. The ratio of their partial pressures is 4:3. The ratio of their atomic masses is. Okay, so given this information that the densities are in the ratio 2:3 and the ratio of partial pressures is 4:3, we have to find the ratio of their atomic masses. So in fact, when the ratio of their partial pressures is 4:3, it means that the number of moles of 1 by number of moles of 2, N1 by N2, is 4/3. And this is coming from the ideal gas equation. We know PV is equal to nRT, and from that we can see that the partial pressure is directly proportional to the number of moles of the gas. So now N1 by N2, so what is N1? N1 is mass of the first one. So if mass is, let's say, M1, so M1 by capital M1, well, M1 is the total mass of the first gas and capital M1 is the atomic mass of first one, right? So 4/3 will be in this ratio, small m1 by capital M1 and divided by small m2 by capital M2. So capital M2 goes up, and let's further write the expression on the right hand side is written in this form. So M1 by M2. Now it says this is, say, M1 by M2. Now what we have is that the densities are in the ratio 2:3. That means M1 by V into M2 by V, where V is the volume, is simply equal to 2/3. So that means small m1 by small m2 can be put as 2/3. So this gives us 4/3 is equal to capital M2 by capital M1 into 2/3, or M1 by M2, which is what we want, is 1/2. So that means for question 13, option 1 is correct. Let's go to the next question now. Question 14 says an ideal gas is taken through the process TV is equal to constant, where T is temperature and V is the volume. Then which of the following graphs shows the correct relationship between pressure and density? Well, the equation is given as TV is equal to constant, and let's try to get rid of T by using the equation PV is equal to nRT. So that means we effectively have P into V square is a constant. If we substitute T is equal to PV by NR in this equation, this is what we are going to get. So PV square is equal to constant, and we have to get a relation between P and density. So we can say that P into density is mass by volume. So volume can be written as mass by density. So that means mass by density whole square is a constant, right? So P into mass by density square is a constant, or since mass is going to be constant anyway, so basically we have P is proportional to rho square. In fact, the given equation transforms to P is proportional to rho square, And among all the graphs, option 4 is matching with this equation. So option 4 is correct for question 14. Let's go to the next question now. Question 15 says, starting from same point A, three ideal gases 1, 2 and 3 are adiabatically compressed. If F1, F2 and F3 are degrees of freedom of 1, 2 and 3 respectively, select the correct option. Well, all three processes represent adiabatic compression. It's clearly given in the question. And well, we have to find a relation between the degrees of freedom of the gas. Now, we know that the slope of PV graph for an adiabatic process, dP by dV for an adiabatic process is simply minus gamma P by V. So that means the steepest graph has highest value of gamma. So that means gamma for 1 is greater than gamma for 2, which is greater than gamma for 3, where gamma is the adiabatic exponent. Well, to get the expression for gamma in terms of degree of freedom, we can write here that gamma is Fr by 2 plus R, that is Cp, divided by Cv, which is F by 2R, and that means it is equal to 1 plus 2 by F. So we have gamma is equal to 1 plus 2 by F. F is the degree of freedom and gamma is the adiabatic exponent. Now it's very clear that as the value of degree of freedom increases, the value of gamma decreases. So that means we can very clearly say that F1 is less than F2 is less than F3 as far as the given graph is concerned. And so that means option 4, which is F3 is greater than F2 is greater than F1, is correct among the given options. So for question 15, option 4 is correct. Let's go to the next question now.